Hello, quick video on complex numbers and polar form. In the first introductory video, we looked at complex numbers in Cartesian form, and we called that Z is the complex number and X is the real part, and Y is the imaginary part. And when we started multiplying together, we got some very strange answers. And by working in polars, I think we'll see a much simpler idea arising from it. So here's converting into polar form. So here we've got a complex number Z. It's got a magnitude or modulus. The modulus is called for the magnitude of our vector here is r, and in polar form, so that's the square root of x squared plus y squared, and we have an angle which is called in complex numbers the argument, theta, which comes up from the real axis and is positive in the anti-clockwise direction, just like ordinary polars, and it goes from minus pi to plus pi, and therefore theta is the arctan of y over x. Now, why is the world going to get a lot easier for us? If we took our number, let's just a little bit of introduction. If we started with a number here, x equals 1, and we multiply it by minus 1, we end up at minus 1, yeah? And effectively, we've taken that number, gone round our unit circle 180 degrees, yeah? Okay, so we can consider these sort of multiplications as being a form of a rotation. Let's now start with our complex number I, yeah? And effectively, we've gone round our circle here, and we 90 degrees. Now, if we multiply I by itself, we get minus 1. So we end up over here, don't we? And effectively, we've gone round our unit circle 180 degrees. So I squared, or I times I, in effect, we doubled our angle, didn't we, from 90 degrees going round, or pi by 2, all the way round to pi, yeah? So actually what we're going to find in a sec is that multiplying complex numbers has the effect of adding the angles. So let's do a little proof of that, shall we? Okay, let's take a generalized unit complex numbers, two complex numbers. Unit in that their length is 1, because I just want to keep our world simple. So Z1 has angle theta 1, so therefore the real part's going to be cos theta, and the imaginary part's going to be sine theta, yeah? And then we're going to take Z2, which is going to have angle theta 2. So we're going to have a cos theta plus I sine theta 2, yeah? Now, if we just multiply these two complex numbers together, we just end up with our two brackets. Yeah, here's our first complex number times our second one. So we're going to have 4 terms, aren't we? So we're going to have our two, I'm just doing it starting with this term here on the left. So I'm going to get a cos times the first thing, cos, and then we get cos times I sine theta, yeah? And then for my second term here, I'm going to get I sine theta cos theta, and I sine theta on I sine theta 2. Now here I've got an I in here and another I there, and we can change the order here of our multiplications. That's no different, it's commutative. So I times I is going to be I squared, so we're going to get a minus 1 come up here, and now that final term is going to become a real term, isn't it? Because the I squared's disappeared for a minus 1. So I've now got a real first term, an imaginary second term, an imaginary third term, and a real fourth term. Okay, and if we group those up for the reals, so we've got a cos minus a sine here for the real. Now some of you will identify that from your angle identities, that cos of theta 1 times cos theta 2 minus sine theta 1 times sine theta 2 is going to be cos of theta 1 plus theta 2. And in the imaginary part, we've got a cos sine plus a sine cos, which those of you know your angle identities will recognize that as being sine theta 1 plus theta 2, yeah? So therefore, let's just put a little diagram on here up at the same place. So if I take complex number Z1 and I multiply it by complex number Z2, I end up over here at Z1, Z2. And the interesting thing is that the angle, the argument of Z1, Z2 is going to be the angle, the argument of Z1 plus the argument of Z2, yeah? So effectively we've added those two together as we've gone round our unit circle. So in multiplying complex numbers, we effectively add the angles, the arguments. What happens with division? Let's just have a quick look at this. Excuse me, gone a bit too far there. Okay, Z1 divided by Z2. So there's our Z1, that's divided by our Z2. And I could write them one over the other as a fraction here, can't I? Now, what do I need to do? I've got complex base. I want to rationalize that. So I multiply it by its conjugate. And if I multiply the bottom by the conjugate, I've got to multiply the top by its conjugate. Now I've got a bit of work to do multiplying out these brackets. Well, top bracket here, if we multiply out, and the real parts as we did before, this time we've got a cos theta 1 times cos theta 2 plus a sine theta 1 sine theta 2, which a lot of you will recognize that as being the angle identity, that is cos theta 1 minus theta 2, yeah? Then if we look at the imaginary part, we've now got a sine theta 1 cos theta 2 and a minus cos theta 1 sine theta 2, which you'll recognize as being sine theta 1 and minus sine theta 2. So looks very similar to what we had before, except rather than adding the angles, we're taking the second angle away from the first. What happens on the bottom? Well, in our conjugate multiplication, we're getting cos theta 2 times cos theta 2 plus sine theta 2 plus sine theta 2, which of course is cos squared theta 2 plus sine squared theta 2. And we know there's an identity for that the cos squared plus the sine squared through Pythagoras equals 1. Look at the imaginary part, we've got sine theta 2 cos theta 2, take away cos theta 2 sine theta 2, so that's going to be 0, isn't it? And that's what we wanted to do, we wanted to get rid of the imaginary part. So our denominator is effectively 1, so all we have to do is just to write that out now without the base, isn't it? So Z1 over Z2 is cos theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So what's that telling us? Well, the angle of Z1, the argument, the angle Z1 divided by Z2 is the argument of Z1, the angle of Z1, subtract the angle of Z2, the argument of Z2. Yep, so if we start off at Z1 and we divide by this smaller angle here, Z2, so in effect we're just going to move our point down round because we've taken off theta 1. That gives us our quotient. So there we are. Okay, we've dealt now with what's happening with the angles. Let's have a quick look at what happens to the modulus. So let's no longer have a unit complex number. This one is the same complex number we had before, Z1, except we're going to give it a modulus, effectively a magnitude of R1, and this one's going to have a magnitude of R2. So if we multiply these together, Z1, Z2, there we go, we're just writing out those two that we're multiplying together. And of course we can just move the R1 and R2. It's exactly the same as we did before, except we've got the R1 and R2, which we can move out to the front. And there's our bracket as we had before in our last calculation. And we know that that's got a magnitude, this complex number here has got a magnitude of 1, don't we? Therefore, the magnitude of Z1, Z2 times Z2, modulus of that, is going to be R1 times R2, and therefore the modulus of Z1, Z2 equals the modulus of Z1 times the modulus of Z2. What happens if we're dividing? Well, Z1 divided by Z2, we've now got our R1 at the front here and our R2 in the division there, so it's R1 over R2, and everything else that we did before will fall apart, but we know that these are both unit complex numbers, so we could go through and get rid of those and do all the calculations we did earlier, but I'm just going to leave them as they are. So we know therefore that the magnitude of Z1 divided by Z2 is just R1 over R2, because everything over here is just unit 1. So therefore the modulus or magnitude of Z1 divided by Z2 is the modulus of Z1 divided by the modulus of Z2. So here we are in summary. If we're working in polar forms, we need to find the modulus or magnitude of our complex number and the argument or angle of our complex number here. And if we multiply them together, then we find that the moduluses of our two complex numbers are just multiplied, and of course we do division, they're just one divided by the other. But more importantly, the argument, the angle for the multiplied z1, z2 is just going to be the argument or angle of the first complex number plus the argument or angle of the second complex number. And if we're doing division, then the argument of the z1 over z2 complex number is just going to be the argument or angle of the first complex number, take away the argument angle of the second complex number. And that all fits in naturally with the idea that if we started off with our point I and we multiply it by it, so which has got an angle effectively of 90 degrees here, and we multiply it by itself, we end up at -1, that fits in, and our angle is we've rotated around 180 degrees or pi. Yeah, so we've effectively added the angles together and doubled them. So I hope that's of use to you.